So as you've been going through the different circuit videos that I've been posting, hopefully you've noticed that there's two rules that I keep bringing up. Technically, these do have a name. They're called Kirchhoff's rules or laws. And they're both conservation rules of some sort. I'll go through them again, and we are also going to look at some circuits where we must use these rules because there is not actually a way to find an equivalent resistance or capacitance. So one of these is the junction rule or law. So let me just draw a basic circuit here. I haven't given them an official name as I was talking them through. The junction rule or law has to do with current flow. This is the conservation of charge is ultimately what this is related to. And technically the flowing of charge. So as we've been talking, we have current that will flow out of the battery or back into the battery. I'm going to call this an I1. But here it reaches a junction. So flowing out of the battery, it goes through resistor 1. But when it reaches this junction, it will split. Some of that current will travel down through resistor 2, but some of that current will travel down through resistor 3. But both current 2 and 3 reach back to this junction and combine back together to become I1. So this junction rule allows us to write an equation relating these currents. So at the top junction, we would say that current 1, that's the arrow pointing towards this junction right here, that current splits up and continues as I2 plus I3. So I2 and I3 break off, but they were once together as I1. And so the conservation is I1, this current that is flowing, is still flowing. It's just that some of it went through resistor 2 and the rest went through resistor 3. At this bottom junction, we get the same equation. We say I2 and I3 are both coming towards this junction and they're going to combine back together to become current 1. Excuse me. So we get this relationship between the currents. This is a conservation rule because whatever current was coming in or towards the junction has to still be flowing out somehow. The top equation, the current coming in was I1. It continued, split into two parts, but it continued as I2 and I3. And similarly, in the bottom, for the bottom junction, I2 and I3 were coming towards the junction, and they combined together to become I1 again. So this junction rule or law tells us that if we add up, so summation, all of the currents flowing in towards a junction, they have to equal the summation of all the currents flowing out of the junction. We have to have the same amount of current in and out. Just like, what's another example? A traffic jam, whether we have no one can sit at the intersection and stay forever. Okay, that's not a great example. Sorry, that's all that came to my mind at the moment. Okay, the other rule or law is called the loop rule or law. And that has to do with potential differences. This is related to conservation of energy. It's not energy in and of itself, but that's the conservation rule that it's related to. If we go back and think about the path, as we talked about capacitors and resistors, I said take a path from one end of the battery to another. As we follow that path, for example, let me get a different color here. If I follow the battery, I know I pass through R1. If I turn here, I pass through R2, and that will get me back to the other side of the battery. The way I've approached this before is I said the battery voltage in turn then has to be shared between those two resistors I passed by. That's a V. Similarly, I could have taken the path that takes me through R1 and then through R3 and back to the other end. And so we could say the battery voltage then would be shared between resistor 1 and resistor 3. Now, when we write this in terms of Kirchhoff's rules, it's written a little bit differently. It says, if we add or sum up all of the potential differences across every single element in a loop, then they need to add up to be 0. Okay, so to change that for our circuit, let me redraw the circuit quickly so that it looks clean. So same circuit, R1, R2, R3, what this rule says, let me draw my currents in again. So I1 represents the one coming in and out of the battery. I2 is the one that comes through R2. I3 is the one that comes this way through R3. So this loop law or rule is saying, okay, if I start at a specific point in my circuit, let's see, what color? I haven't used black. Let's go with black here. The loop rule is telling me I just have to make a complete loop. So I can choose any location in the circuit to start at, and I'm just choosing this bottom left corner because it's there. I'm not in any way saying I have to start at this bottom left corner. But if I follow a loop starting at this bottom left corner, go all the way around and get back and end also at this bottom left corner, then all the voltages, these are potential differences, delta V's, then they must add up to be 0. This is another way of describing what we did before. Okay, now in physics we literally add potential gains and subtract potential drops. I'm mentioning that in terms of, for anyone who's had the EE classes, even just the basic class, they add drops and subtract gains, just backwards. They're equivalent equations though. So here, my path, I'm gonna just go up. I am passing from this short end of the battery that is negative. I cross over to the positive end of this battery. Since I'm going this way, I see an increase in the battery voltage. That's just based off of the direction I have chosen to follow my path. As I continue, the next thing I come to is this resistor. This resistor will have a potential difference across it because it has current flowing through it. Now we're using the definition of current flow as if it were positive charges. The current direction is the same direction as the electric field. That means this particular resistor would be higher potential at the left end and lower potential at the right end. So if my path is taking me left to right with the current, I'm going to see a decrease of a delta V1 as I pass by. So the potential difference I see is delta V1. I'm seeing a drop because I'm going with the current, high to low. Now my path can take me down through this middle resistor. I'm going to see a potential difference of delta V2. Similarly, because I'm going with the current flows high potential to low, I'm going to see a decrease of a delta V2. As I finish my path, that gets me back to where I started. The delta V between start and end is 0 because I'm getting back to the exact same potential. So I set this equation, finish the equation, I should say, and set these voltages, these gain in the battery and then the drops from the resistors, I set that all equal to 0, which though gives us that first equation when we talked about the battery puts in the EMF, the elements we pass by will then use a portion or have a portion of that EMF. So this loop rule, the difference between what we did before and what we're doing now is that we're going to start and end at the same location, and thus the difference overall will be 0. And so all the delta V's we see will be on the same side. The other delta V we could look at, let's say I started down here, bottom right corner. So I'm going to start and end here. And it doesn't matter which way I follow a loop. In terms of this loop rule, the only thing that truly matters is that I start and end at the same location. So let's go and take our path around the outside perimeter. That's a loop. So the whole outside loop. And let's go counterclockwise this time. Okay, let me make this a little bigger so we can see my path. So my path, I'm going this way. The first element I pass by is R3. It's going to have a potential difference of delta V3. But unlike our first loop, this time I'm going opposite the current. My path is opposite. Current flows high to low. If my path takes me opposite the current, I'm going to see an increase in potential. So a positive delta V3. Let me move this a little bit so I have more room. Okay, my path. If I'm doing the whole outside loop, the next thing I come to is resistor 1. I'm traveling to the left, opposite the current. If our path takes us opposite the current, we're going to see an increase of that voltage, delta V1. As I continue, I come to this battery, but this time I'm going this way, high to low. So I'm going to see a decrease of the battery voltage. I have my path, I got to keep going until I get back to where I started. When I'm back to where I started, I then finish this out, and my equation has to equal 0. Notice this equation is this equation up here, back when we were talking about battery puts the voltage in and the elements take the voltage out. The loop rule, we are looking specifically at potential differences. So the biggest part of the loop rule is to make sure we start and end. So start and end at the same point, because that's how we get the delta V equals 0. We're adding or subtracting delta V's. So if it's a resistor or a battery, it could even potentially be a capacitor. We'll look at capacitors as well. We're looking specifically at the delta V's. This is always potential. So if our path we're taking, our loop, if we path in the same direction as current, delta V for the resistor will be negative. I guess I need to put B, negative. If the path is the opposite the current, delta V for the resistor will be positive. For the battery, it's based off of which plate we see last. So with batteries, the long end represents the positive end, the higher potential. The short end represents the negative or lower potential. So it just, whichever plate we see last as we pass by will determine the sign. Okay, capacitors we'll talk about later as well. It has to do with the positive versus negative plate of the capacitor. But for now, our problems will involve resistors and batteries. Okay, we're going to go through a few examples. I'll do those in separate videos so that you can look at them individually. But again, these are the rules we will be using.